Welcome to my classroom. Continuing with the topic soil genesis, today we will discuss pedogenic processes. Last time, if you remember, I told you that soil formation occurs under two type of processes and factors. One is the factors responsible for soil formation, another is the processes responsible for soil formation. So soil formation processes, these are nothing but pedogenic processes are in fact the soil forming processes. Soil forming processes. So these are very complex and dynamic in nature. These processes are complex. Why complex? Because all these processes maybe they may act in combination of two or more than two processes simultaneously. So that's why we call this as complex. So and dynamic. Dynamic means these processes, since these are being carried out continuously over a period of time. That's why if you remember, time was a factor, an important soil forming factor, soil formation factor. So that's why we say that these processes always remain changing, dynamic, because one process is affected by another process, or one process is affected by a set of soil forming factors. So and second thing is that yes, these soil forming processes are responsible for converting parent material into a mature soil. When we say mature soil, that is, there is distinct formation of A, B and C horizons. A, B and C horizons. And this, the time period taken for this conversion of parent material to a distinct or mature soil, it's a long process. But not as long, I should say these are faster than the geological processes. Now geological processes, I should say, are, for example, the process whereby it is upliftment of earth at certain points, formation of mountains, formation of rivers. So these processes, in fact geological processes, are very long term process. It may take millions of years for the formation of if I say Himalayas, they were formed over millions of years. In contrast to geological processes, these pedogenic processes are faster, and these may not be faster from human life point of view. Human lifetime. So if I say that I'm going to survive for 100 years, so that doesn't mean that I may see that, okay, this parent material has been converted into a soil. From human point of view, these may not be faster, but in comparison to geological processes, these pedogenic processes are faster. So they may also take thousands of years, maybe tens of thousands of years to convert parent material into a mature soil. And of course, as I told you, that these processes act under a set of, better I should call, environmental conditions or set of soil forming processes. Soil forming factors. And those factors, you remember, these are climate, vegetation, relief, time, parent material, of course. So now these pedogenic processes are based on some basic processes. So what are those basic processes of pedogenesis? Should I call it as pedogenesis? And those basic processes are: number one, addition or gain of mineral and organic matter in the soil, or you can say whatever parent material is there. It could be gain of these materials, mineral matter, organic matter, because a process will not start until and unless there is parent material. And parent material may comprise of mineral matter, it may comprise of organic matter. Then there could be loss of mineral and organic matter from the soil. And when I say here from the soil, here I should say into the soil. That means it's not a mature soil, so it is in the process of formation. So either addition or loss. And third is transformation of mineral and organic matter within the soil. Because once there is gain of mineral matter or organic matter, then it gets transformed. Instead of, I should say, processes, just came to my mind this thought that why not to call it as basic principles. Basic principles of pedogenesis. So, addition, gain of mineral and organic matter, loss of mineral organic matter, then transformation of mineral and organic matter into, here I should say, from complex to simpler forms. And third is then translocation of simpler constituents of mineral and organic matter. So this translocation could be from one part of the landscape to the other part, maybe from higher reaches to the lower reaches. It could be with water. Similarly, on the same level ground with wind, these could be transported from one part to another part and deposited somewhere. Or these could be within the soil, from one layer to another layer, what you call as alluviation, that is loss, illuviation, that is gain. So these are the four basic principles: addition, loss, transformation, translocation. Now let us discuss what are the pedogenic processes. Pedogenic processes, in fact, can be classified into two groups. One is fundamental pedogenic processes. And second is specific pedogenic processes. Now, what are the fundamental pedogenic processes? These are found in all type of soils. Those fundamental, or you can say basic soil processes, they have to happen in all type of soils under all the environmental or soil forming factors. And these basically provide a skeleton for the specific pedogenous processes to occur. So these happen in all the soils. and these provide a skeleton for specific pedogenic processes to occur. Now specific pedogenic processes, again these are of two types. One is zonal and another interzonal. Now zonal, these are basically the specific pedogenic processes which occur under the prevailing conditions, of two active soil forming factors. What are those two active soil forming factors? Climate and vegetation. Of climate and vegetation. So those processes which are influenced by the I should say more by the active processes, active soil forming factors, they are called zonal. And interzonal, these are the pedogenic processes which occur, or you can say which are influenced more by parent material and relief. And you know what is relief? It's topography. So these are the passive factors. So zonal, which are influenced by active factors, interzonal, which are affected by the passive factors. Now we will discuss these factors one by one. So first of all, we will discuss zonal and then interzonal. So the first pedogenic specific, okay, before specific we will also discuss the fundamental. So the fundamental processes are, the first one, fundamental. Pedogenic processes, as I told you, these happen in all the soils and these act as skeleton for the various specific pedogenic processes. So here the first one is humification. As the name suggests, this process mineralizes the organic matter into simpler compounds. So here it is the process of transformation of organic materials into humus. Humus, basically they call it as end product, but actually it's not the end product, but yes, it is much more resistant to the microbial activity as compared to the intermediate products of organic materials or organic materials themselves. So here, when we add organic matter into the soil, it gets decomposed and this decomposition takes place by various microorganisms, and ultimately you have the formation of organic acids, simple organic acids. So organic matter is broken down or decomposed by microbial organisms into simple organic acids. Then these simple organic acids, they are polymerized. So simple organic acids, they get polymerized and this polymerization again is because of the bacteria. So it is bacterial polymerization. So due to the bacterial polymerization, simple organic acids are converted into some colloidal like substances. Actually, let me call it as not colloidal like but colloidal substances, what we call as humus, which is more resistant to the further microbial activity or microbial decomposition. So this whole process, it depends upon the environmental conditions, the temperature, moisture, rainfall, and it may take up to 1 year conversion of organic matter to humus. But in fact, it's not that we have today we have added the organic matter and we will wait for 1 year or so to get the humus. So this process is a continuous process. We go on adding organic matter and organic matter. At a particular time in the soil, you will find organic material undecomposed, slightly decomposed, intermediate decomposition process, and ultimately you may find humus. So continuously the humus remains formed, and over here you are adding continuously the organic matter, maybe through natural processes, maybe through root biomass, through addition of crop residues, something like that. So this process continues, and if you say that you had added organic material, after 1 year you may have say this much of humus, and then don't expect this humus will remain there in the soil. This humus, of course, it also decomposes, but at a very, very slow rate. So if you don't add more organic material into the soil, this humus, or what you call as organic carbon, it also starts getting reduced, its content gets reduced in the soil. So this is first fundamental process. Second is alluviation. When we say alluviation, starting with the alphabet E, so it means loss of simpler constituents of mineral and organic matter, and these could be humus itself, these could be clay particles, clay oblique even silt particles, and these could be various anions, I should say, like sulfate, calcium, sodium, sulfate, calcium, sodium, carbonates, magnesium, potassium, then silica, etc. So mineral, simpler constituents of mineral matter as well as organic matter, and again clay and silt particle, these are also the simpler constituents of mineral matter. So they get lost from one layer to another, and again, as I said, from one point to another point, maybe from higher to lower, or maybe at the same elevation with the wind, with water. So this is how the process of alluviation. And when it is within the soil, so the layer through which these get lost, out of which these get lost, that layer is called alluvial horizon. E-L-U-V-I-A-L, alluvial horizon, representing the loss of the simpler constituents of mineral matter and organic matter. Then apart from this, next is third process is alluviation, and alluviation means the reverse of this. If alluviation is lost, then it will be gain, because whatever is lost at one point, so this is gain of simpler constituent, same those will be gained by the lower layers. Then we call this as alluvial horizon, from where the material from upper layers has been deposited, and at one point where the material at the surface has been translocated, deposited at another point, then again you call it as alluvial soils. So these three were the fundamental pedogenic process. So after this, we have the specific pedogenic processes. Specific, as I told you, the specific pedogenous processes, they act more under the influence of what you call as soil forming factors. So specific pedogenic processes, and here the first one is calcification. As the name suggests, it is the deposition of calcium compounds. So it is process of precipitation and accumulation of calcium compounds in different layers. Now the question is how the calcium compounds they get precipitated. So it is because of the acidification of water. Under high carbon dioxide conditions, water plus carbon dioxide, these react together to form carbonic acid. Okay, and then this carbonic acid it solubilizes calcium carbonate. Now this calcium carbonate is insoluble, so it reacts with carbonic acid to form calcium bicarbonate. This is soluble in nature. So this calcium bicarbonate under the condition, now this was that carbon dioxide level should be there, because only then carbonic acid will form, and carbonic acid will solubilize calcium carbonate, insoluble calcium carbonate, and ultimately this soluble calcium compound, it will remain in the soil till there is appropriate sufficient level of carbon dioxide. And once carbon dioxide level decreases and temperature increases, then what happens that this calcium bicarbonate, this again gets converted into calcium carbonate plus water plus carbon dioxide. So now this again is insoluble. So when carbon dioxide level decreases, sufficiently decrease in carbon dioxide level, it results in the formation of calcium carbonate, and this will be in the form of small concretions. So here this will get precipitated. It is precipitated in the form of small concretions, and you have a horizon which is called calcic horizon is formed, and this is not good for the roots of the plants. So this is how we say that calcification of a particular soil horizon takes place, resulting in the formation of a horizon which is called calcic horizon, having very high content of calcium. Not only high content but also very strong spiny calcium nodules, calcium carbonate nodules, and what we call as concretions. So this is one process, specific process. Second is decalcification. Decalcification. Now decalcification, as I said, it is the reverse of calcium. That means solubilization of accumulated calcium carbonate. So what happens now that again this reaction, calcium carbonate then reacts with again with water. You can see it is the reverse of this reaction, water plus carbon dioxide, but the condition is that the carbon dioxide concentration should be higher, and of course the temperature should also be higher for this reaction to take place, and it results in the formation of calcium bicarbonate. And this calcium bicarbonate, being soluble in nature, it leaches out of, this is soluble and it gets leached, and your horizon, it gets decalcified. So simple, very simple. And then next process is podzolization. Podzolization. This is in fact from the Greek word what you call as pod, means under, and zola, it means ash like, just like the color of ash, color or structure of ash. Now what happens in podzolization, that the cations, we have a weathering process. During weathering, the cations which are released, I should say released cations, they leach out. But you will ask me the question that why these cations leach out. So here the condition is podzolization. So I should say conditions for this process takes place under cold climate, cold and humid climate, where you have the vegetation that is coniferous, and coniferous vegetation is of acidic nature. And the parent material is sandy. These are the conditions. Parent material is sandy. So cold and humid, so high rainfall, plus sandy nature of the parent material, because when we say sandy nature, that means it has dominance of macropores, bigger pores, which facilitate the movement of the cations or smaller soil particles like clay, silt, with the help of water, and water comes from high rainfall plus sandy nature. This leads to the leaching. So this leaching is due to, I should say, again right over here, high rainfall plus sandy parent material. And when this bases, particularly the cations, when they leach out, they decrease the pH. So pH becomes less than 5. So because of the leaching out of the cations, the pH decreases, and then when pH decreases, then the organic acids, or what I should say, the organic acids, they should get polymerization. So this polymerization, in fact, it is very slow. Why it is slow? Because of the acidic environment acidic conditions and cold conditions. So because of these two, the polymerization of organic acids is less, it is slow. And when organic acids, they are not polymerized, then these organic acids, they move to lower layers. So this is a very interesting process, and these are deposited in B horizon. So B horizon is below E horizon. And the silica, what remains now above, because it's sandy in nature, dominance of silica, and silica remains in B horizon or upper B horizon, remains in E horizon, sorry, E horizon. Why? Because it is insoluble in nature. And this silica, in fact, this gives a ash-like, because silica particles, they are just like sand particles, they are not flocculated, non-flocculated. So they give ash-like tinge. Ash-like tinge to what? To E horizon. E horizon. We also call this as podzolic horizon. So in nutshell, podzols are created in the conditions where there is cold and humid climate. Vegetation is coniferous, which is acidic in nature. Parent material is mostly sandy, that is silicaceous, I should say siliceous. So because of high rainfall and sandy nature, the organic acids, they move, their polymerization is less because of the acidic conditions, cold conditions, microbial activity is sluggish. So here it's very important that these cold and acidic conditions, these lead to sluggish microbial activity, better called as bacterial activity. So polymerization is very slow, and that's why these organic acids, they move down to lower layers B horizon. So what remains in the upper E horizon? That is silica, because it is comparatively insoluble, and this is non-flocculated. So this gives an ash-like tinge to the horizon, which is called podzolic horizon, and the process is called podzolization. I hope it's clear. After podzolization, we have the next process. Sorry. So the next process is laterization. Now what happens in laterization? Again here it's, better discuss the conditions. Conditions here are warm and humid climate, broadleaf vegetation, and this broadleaf vegetation, it has basic character, it's not acidic, coniferous, it has acidic character, and parent material is basic parent material, that's high in iron. Parent material is basic in nature, iron content is high. So under such situations, now what happens, that because it is warm and humid conditions, so high rainfall, these cations, they get leached out due to high rainfall conditions. So intense leaching of basic cations, because the nature of the parent material is again basic, and but still the pH, it remains from neutral to alkaline. Now here a point should come to your mind that if there is intensive leaching, then why doesn't the pH get reduced? It is because of the basic nature of the parent material, that pH, yes, it is reduced, but it doesn't go below 7. So the pH remains from neutral to alkaline. And what happens then under alkaline conditions? Under such conditions, the silica gets solubilized, so it becomes silica is soluble at pH more than 7. That is under alkaline condition. So if silica is soluble, it leaches out of the profile. So first of all, the cations, because of high rainfall conditions, there is intensive leaching out, and pH still remains neutral to alkaline because of basic nature of vegetation. And under alkaline conditions, the silica which is present in the soil, it gets solubilized under alkaline conditions, and when it solubilizes, it starts leaching. It comes in the solution form, so leaching is there. So the sesquioxides, then, as I said, iron and aluminium. So sesquioxides, they remain in the upper horizon. So silica has leached down. In podzolic soils, it was reverse the case. Low pH, so silica, the cations, they washed out, and ultimately the silica, it remained at the surface, giving a ash-like tinge to the soil. But here silica moves down because it gets solubilized under high pH conditions. Sesquioxides remain in the upper horizon, and these iron and aluminium oxides, they impart red color to soil particles. I should say better this. And what we call as this will be then we call laterite soil. So laterite soils are those which are high in sesquioxides, reddish in color, could be coarse grain, could be fine grain. If it's fine grain, we call it as lateritic. Lateritic. When it is fine grained, and we call it as laterite if it is coarse grained. And the process is called laterization. I hope it's clear. The next process is gleization. You might be a bit astonished that I'm using a very simple blackboard and a cloth duster, because I'm very conservative in nature. I'm not spending too much on this recording system. I have a simple webcam and a program on the laptop, because my objective is not to earn money by making very hi-fi lectures. My objective is to impart my knowledge to the younger faculty, to the students, UG, PG students. And if I'm really successful in doing so, I'll be more than happy. So I hope you are not annoyed by this type of, the simple things I'm doing. So anyhow, next process is gleization. Gleization, first I should define the conditions. So the conditions are, it occurs in, before that, glee means this is again a Greek word, glei, G-L-E-I. It means blue, green or greyish color. Means either it may have bluish tinge or green tinge or greyish tinge, that we call as glei, and the process is gleization. So here the conditions are poor drainage, could be high rainfall, could be low rainfall also, but even during low rainfall conditions also, if it's a depression type of the landscape, then drainage will be poor. So poor drainage, impervious parent material, and lack of, yes, of course, if it's impervious, then it will be lack of aeration. So what happens under such conditions, that when you have poor drainage condition, aeration, oxygen content will be low. So oxygen content will be low, and under depleted oxygen conditions or low oxygen conditions, under low oxygen conditions, this ferric form, that is ferric cation, it will be converted into ferrous. And the ferrous compounds, these are soluble, and these form ferromagnesium. These form organocomplexes, ferrous organocomplexes. And of course it is soluble. So this is also the form which is available to the plants for the plant roots. So they come into solution, and then there is leaching, and resulting in typical, because I should not say leaching, because most of, if it's ferric form, it will impart red color to the soil particles or parent material. But when it becomes ferrous, so it could be ferrous plus ferric plus organocomplexes, or it could be only ferrous. But again, the ferrous is dominant, and the ferrous has a blue color, sort of, like you have ferrous sulfate, it's completely blue in color. So when this ferric gets converted into ferrous, it gives a slight grayish, blue or greenish tinge to the soil particles, and we call glazed horizon. But again, if it is under, say, the situation is like this is your soil surface, and here you have a water table, and here say it is poor drainage or poor oxygen, and you have the formation of, or you have a process of gleization or glazed horizon, then this water table, if after the during dry period, it may move down. When it moves down, then here you may have oxidized conditions, or I should say good oxygen. And if oxygen increases somehow in parts, so wherever you have the high oxygen content, then you may get converted, ferrous may get converted into ferric form, and this ferric then gives a brownish or reddish tinge. So in such type of glazed horizons, because of fluctuation in the water table, you may find the small patches of brownish color or small patches of reddish color in sort of blue or green or grayish color horizon. So that is because of the fluctuation in the water table. If this is this gleization process has been under the influence of shallow water table, then you may find this type of situation. Otherwise, if it's a continuously poor drainage conditions, impervious parent material, then of course you will have the dominance of the process of glycation and glazed horizon. So after glycation, the next process is salinization. So this is number 6, salinization. So as the name indicates, formation of saline soils. So what are the conditions over here? So as far as climate is concerned, so this is arid and semi-arid regions. So this is basically the accumulation of salts. What is salinization? Process of accumulation of salts in different layers. So as I said that in arid and semi-arid regions, and particularly, yes, I can also say shallow water table conditions, or you can say under poor drainage conditions. So if this is shallow water table, this is your soil surface. So what happens that, and this is your capillary fringe. So here the water, it rises up through the process of capillarity, reaches the surface, gets evaporated, and the salts which are being carried by this water, these salts get accumulated at the surface. This is salt accumulation. Because under arid and semi-arid conditions, we have very high evaporation rates. And through process of capillarity, the water from shallow water table, it rises up at the surface, gets evaporated, salts get accumulated, resulting in the formation of saline horizon or saline soils. And the process is called salinization. And yes, because in saline soils the osmotic potential is high and there is excess soluble salts, and when osmotic potential is high, even if water is present in the soil, it cannot be taken up by the plant roots because of high osmotic potential, and there could be the deficiency of water and nutrients under such conditions. And next process is alkalization. Alkalization, better I should say, rewrite it, alkalization. So the word alkali means sodium potassium. So it is a process of accumulation of sodium salts in the surface of soil. I'm sorry to just before I go for this, under salinization, when I say salinization, when I say it is accumulation of salts, that means the electrical conductivity of the saturation extract is more than 4 decisiemens per minute. 4 decisiemens per minute. And yes, pH is less than 8.5, and exchangeable sodium percentage is also less than 15. So these are the conditions when you have such type of soils. So we say these are saline soils. So here now the pH, when there is accumulation of sodium salts at exchange complex, and exchange complex is your clay particles and organic matter, that is clay and betterite humus. So pH increases, it's always higher than 8.5 in alkali soils. So it results in the formation of alkali soils. Now people generally call it as sodic soils. Here let me explain you that many a times I ask this question to even the PG scholars, that what is the difference between, you know, saline, alkaline soils, and immediately they say saline soils are where EC is this, pH is this, and alkaline they say it is you know, the accumulation of sodium salt, pH 8.5. So in fact better not get confused, it is not the alkaline, it is alkali soils. Alkaline means pH more than 7. If pH is less than 7, then acid soils. So acid alkaline soils, saline alkali soils. But yes, that is just to confuse you. Otherwise, if I say saline sodic soils, sodic immediately indicates sodium content. But alkali and alkaline, these are two different soils. So many a times the scholars, they get confused. So here exchangeable sodium percentage is again more than 50. So these are the conditions you know, for the soil to be sold as black. So here what happens that soils, most of the carbonates, they get precipitated and sodium remains in the soil solution. As I said, it gets absorbed on the exchange complex, and this is high pH. It results in dissolution of humus, and it imparts a black color to soil, and that's why we also call it as black alkali. People also call it as white alkali, but I differ over here, because basically the name that confuses the audience. Yes, it is a white crust, a white layer of salts could be seen at the surface or maybe at any layer, but it's not alkali soil. So I have seen in many books people say white alkali and black alkali. Yes, you can call this as black alkali because these are alkali soils or sodic soils. So the last process then is pedoturbation. That is the seventh, pedoturbation. Pedoturbation is basically very simple. It is a mixing of soils. Mixing of soil in various layers. Now the question is, it depends on how these soils gets mixed up. If the mixing is because by the faunal, that means animals they are mixing, like earthworms moving from one layer to another, eating the soil, releasing that in another layer. So that means the two layers get mixed up. So we call this as faunal. So this is by animals. And if pedoturbation is by plants, we call this as floral. If pedoturbation is by swelling and shrinking of clays, swelling, shrinking of clays, that also leads to mixing of soil. We call this as agrilo, I should say, yes, agrili pedoturbation. pedoturbation. And if this mixing is by freezing and thawing process, freezing and thawing, then we call this as cryopedoturbation. CRYO, cryopedoturbation. So that's all. Pedogenic processes. I hope I am able to make the things clear. Thank you very much.